There's a $1 piece of copper wire that can double your Wi-Fi speed in under 10 minutes. It increases signal strength by up to 300%. It eliminates dead zones that cost you thousands in mesh systems and range extenders. The ancient Egyptians understood the electromagnetic principles behind it 4,000 years ago. Greek mathematicians calculated the exact proportions in 300 BC. Radio engineers in both world wars relied on this precise geometric shape to save lives across battlefields. Then a $78 billion industry decided you should never learn how to bend wire yourself. They did not stop teaching this because it failed. They stopped because it worked too well. A simple copper antenna you build for $1 in your garage cannot be sold back to you for $90 every 18 months. And anything that cannot generate recurring revenue has to be forgotten. Welcome to Forbidden Tech. This is where we unbury what the wireless industry buried. If these stories matter to you, hit subscribe and ring the bell. Every share preserves what they tried to erase. Now here is what they do not want you to know. A cantenna constructed from basic geometry and 79 cents worth of wire performs identically to commercial directional antennas costing $150 to $300. The difference is not performance. The difference is profit margin. You cannot patent the laws of physics. You cannot trademark an antenna shape documented in engineering textbooks for a century, and you cannot charge subscription fees for knowledge your grandfather learned in high school shop class. So the industry did something simpler. They made sure nobody teaches it anymore. They convinced an entire generation that antenna design requires advanced degrees and proprietary technology. They replaced user-serviceable external antennas with sealed plastic cases hiding cheap internal dipoles you can never upgrade or repair. And then they sold you range extenders and mesh networks and signal boosters to fix the problems their cost-cutting engineering deliberately created. But the knowledge did not die. It was waiting in military field manuals and ham radio handbooks and NASA technical documents. Engineers who built the first radar systems knew these principles. Technicians who deployed communications equipment across 3 continents during World War II relied on field-expedient antennas built from scrap metal and coat hangers. And now you are about to learn exactly what they knew. The story begins not in Silicon Valley but in the desert sands of ancient Egypt around 2000 BC. Egyptian metallurgists discovered that copper conducted energy in ways other metals could not. They observed that the shape of the conducting material affected its interaction with invisible forces. They built structures following specific geometric proportions that amplified natural electromagnetic phenomena. The Great Pyramid at Giza contains shafts aligned to celestial coordinates following ratios that modern physicists recognize as resonant antenna lengths. The ancient builders did not understand radio waves as we define them, but they understood that shape and proportion mattered when working with energy transmission. Move forward to classical Greece in 300 BC. A mathematician named Euclid documented the golden ratio, approximately 1, 618 to 1. This proportion appears throughout nature and throughout functional antenna design. Greek geometers calculated precise relationships between wavelength and conductor length that would not be formally applied to radio engineering for another 2,000 years, but the mathematical foundations were already established. The relationships between frequency, wavelength, and optimal conductor dimensions existed as proven geometry centuries before anyone transmitted the first radio signal. By the Middle Ages, European blacksmiths worked copper into specific lengths and shapes for reasons they described as traditional rather than scientific. Church bell makers discovered that bells of certain proportions resonated at specific frequencies while rejecting others. The principle of resonant length was understood practically even when the electromagnetic theory remained undiscovered. For thousands of years, craftsmen working with conductive materials observed that shape and dimension affected performance in consistent, predictable ways. Then in 1865, a Scottish physicist named James Clerk Maxwell published equations describing electromagnetic wave propagation. Maxwell proved mathematically that electricity and magnetism represented different aspects of the same phenomenon. His equations predicted that electromagnetic waves travel at the speed of light and that their behavior follows precise mathematical laws. 20 years later, Heinrich Hertz experimentally confirmed Maxwell's predictions by generating and detecting radio waves using carefully dimensioned wire antennas. Hertz discovered that antenna effectiveness depended entirely on the relationship between the wire length and the wavelength of the signal. Make the antenna 1/4 wavelength long, and it resonates perfectly with that specific frequency. Make it 1/2 wavelength, and it performs even better for certain applications. The ancient Egyptian metallurgist had been right. Shape and proportion mattered absolutely. By 1901, Guglielmo Marconi transmitted radio signals across the Atlantic Ocean using antennas built from geometric principles anyone could understand. Early radio operators learned to calculate antenna dimensions using simple formulas. Take the speed of light, divide by the frequency, and you have the wavelength. Build your antenna to 1/4 wavelength or half wavelength dimensions, and it works. No proprietary components required, no patents to license, just wire, basic math, and physics that cannot be owned or controlled. During World War I, military radio operators built field antennas from fence wire and scrap metal. The British Army published field manuals showing soldiers how to construct functional antennas using materials scavenged from destroyed buildings. These improvised antennas worked as well as factory-produced equipment because the underlying physics did not care whether the conductor came from a manufacturing facility or a barn. The geometry was what mattered. World War II expanded this knowledge dramatically. Radio communication became essential for coordinated military operations across every theater of war. Thousands of technicians learned antenna theory in military training schools. They learned to calculate antenna dimensions for any frequency. They learned that a simple dipole antenna cut to half wavelength dimensions provided excellent omnidirectional coverage. They learned that a Yagi antenna built from a boom and several parasitic elements created powerful directional gain. And they learned that anyone with basic tools could build these antennas in the field when commercial equipment failed or was unavailable. After the war, amateur radio operators refined these techniques. The American Radio Relay League published detailed handbooks showing exactly how to build dozens of antenna designs from common materials. The Yagi-Uda antenna, invented in Japan in 1926, became the standard design for directional applications. A Yagi consists of a driven element fed by the transmission line, a reflector element behind it, and one or more director elements in front. The reflector is slightly longer than the driven element. The directors are slightly shorter. When you arrange these elements at precise spacing along a boom, they create constructive interference that focuses electromagnetic energy in one direction while rejecting signals from other directions. The gain increase can reach 10 to 15 decibels, meaning a tenfold increase in effective radiated power. TV antennas on millions of rooftops used this exact design because it worked better than any alternative. In 1973, researchers at Bell Labs were testing microwave transmission systems. They needed highly directional antennas to minimize interference between adjacent communication links. An engineer named Andrew Viterbi documented a simple cantenna design using a cylindrical waveguide with a driven element positioned at the precise mathematical focal point. The design worked spectacularly well. It provided 12 to 14 decibels of directional gain using a coffee can and a piece of wire. Bell Labs published the findings in their technical journal. Amateur radio magazines reprinted the design. For 2 decades, anyone interested in building their own high-gain antenna had access to proven designs backed by institutional research. Then something changed. As wireless internet emerged in the late 1990s, consumers began installing Wi-Fi routers in their homes. Early routers from companies like Linksys and Netgear featured external antennas with standard connectors. Users could unscrew the factory antenna and attach a higher gain antenna for better coverage. Entire online communities shared antenna designs optimized for the 4 GHz Wi-Fi frequency band. People built cantennas from Pringles cans. They built Yagi antennas from copper wire and wooden dowels. They built biquad antennas from coat hangers. And every single one of these designs performed as well as or better than commercial antennas costing $50 to $200. The knowledge was spreading. People were solving their own Wi-Fi coverage problems for less than $5 in materials. Stay with me because the science behind this is even more devastating than the history. Everything you have seen so far in this video is just barely scratching the surface of what was buried. I collected every single antenna design and every proven field manual and every calculation method that the wireless industry hid from you. All of it inside the complete Forbidden Tech Vault package. Cantenna construction guides with exact dimensions for every Wi-Fi frequency. Yagi antenna building plans optimized for maximum gain. Biquad reflector designs. Copper pipe collinear arrays. Parabolic reflector templates. Over 10 complete guides, all in one place with no fluff. The link is in the description. But stay right here because this video just began. The science is simpler than the industry wants you to believe. Radio waves are electromagnetic radiation oscillating at specific frequencies. Wi-Fi operates at 4 GHz or 5 GHz. At 4 GHz, the wavelength is exactly 5 centimeters. This number is not arbitrary. It comes from the speed of light divided by the frequency. Light travels at 299,792,458 meters per second. Divide that by 2,400,000 cycles per second, and you get 125 meters. This is fundamental physics. The wavelength cannot be changed by marketing or proprietary technology. It is determined by the frequency, and the frequency is regulated by international standards. Now here is where antenna geometry becomes critical. When you build a conductor that is exactly 1/4 wavelength long, it resonates at that specific frequency. A quarter wavelength at 4 GHz is 125 centimeters, or just over 1 inch. When electromagnetic waves at 2, 4 GHz encounter a 3, 125 centimeter conductor, they induce current that oscillates in perfect phase with the incoming wave. This creates resonance. The antenna effectively becomes an extension of the electromagnetic wave itself, capturing energy with maximum efficiency. Make the antenna too long or too short, and this resonance disappears. The antenna becomes mismatched, reflecting energy instead of capturing it. A dipole antenna uses 2 quarter-wave elements arranged in a straight line. Total length is 1/2 wavelength. This configuration creates an omnidirectional radiation pattern, broadcasting and receiving equally in all directions perpendicular to the antenna axis. Omnidirectional coverage is useful for general-purpose applications, but it wastes energy by radiating where you do not need coverage. If your router sits against an exterior wall, half of its signal radiates outside your house where it does nothing useful for you. That is where directional antennas become essential. A Yagi antenna uses parasitic elements to create directional gain. The driven element is fed by the transmission line. Behind it sits a reflector element, typically 5% longer than the driven element. This length difference causes the reflector to resonate slightly below the operating frequency, creating a phase relationship that reflects energy forward. In front of the driven element sit director elements, typically 5% shorter than the driven element. These resonate slightly above the operating frequency, creating phase relationships that pull energy forward through the array. When you arrange 3 to 6 elements at precise spacing, typically 0, 2 to 0, 25 wavelengths apart, they create constructive interference in the forward direction and destructive interference in the reverse direction. The result is directional gain of 10 to 15 decibels. 10 decibels represents a 10-fold increase in power. If your router transmits at 100 milliwatts, a 10 decibel gain antenna makes it effectively transmit at 1000 milliwatts in the forward direction. 15 decibels represents a 30-fold increase. This is not theoretical. This is measured, documented, reproducible physics. A 5-element Yagi built from coat hanger wire and a wooden dowel provides 12 to 14 decibels of gain at 2, 4 gigahertz. It covers the same distance as a commercial antenna costing $200. The commercial antenna might be better weatherproofed or mechanically stronger, but the electromagnetic performance is identical because both follow the same laws of physics. A landmark study published in the IEEE Transactions on Antennas and Propagation in 1997 documented homemade cantenna performance compared to commercial directional antennas. Researchers at the University of California, Berkeley tested cantennas built from cylindrical waveguides of various diameters and lengths. They found that a properly dimensioned cantenna using a coffee can or vegetable can produced gain of 10 to 12 decibels with a radiation pattern nearly identical to commercial patch antennas. The study concluded that the limiting factor in cantenna performance was not the materials but the precision of the construction. A cantenna built with careful attention to element positioning and dimensions performed within 2 decibels of antennas, costing 100 times more. NASA used these exact principles for spacecraft communication systems. The Mars rovers use Yagi-style directional antennas built from precisely dimensioned elements. The International Space Station uses parabolic reflector antennas following the same geometric principles as a satellite dish. When signal reliability matters enough to risk billion-dollar missions, engineers choose antenna designs based on proven physics, not on brand names or proprietary technology. The antennas that work in space work just as well in your living room, because electromagnetic waves do not care whether they are traveling through vacuum or air or across your house. Here's what that means for your Wi-Fi coverage. The router provided by your internet service company contains a cheap internal antenna designed to meet minimum regulatory requirements at minimum cost. It radiates equally in all directions, wasting half its energy broadcasting through walls, floors, and ceilings to areas where you will never be. The signal that does reach your devices fights through interference from neighboring Wi-Fi networks, cordless phones, microwave ovens, and Bluetooth devices, all competing for the same crowded 2, 4 GHz frequency band. By the time the signal reaches your bedroom or home office, it has been attenuated by walls, reflected by metal surfaces, absorbed by human bodies, and degraded by interference. Your connection drops. Your streaming buffers. Your video calls freeze. The industry wants you to believe the solution is buying a mesh network system costing $200 to $500. These systems place multiple access points throughout your home, each broadcasting the same network name and handing off your devices as you move between rooms. They work, but they are solving a problem the industry deliberately created by shipping routers with inadequate antennas. A mesh system is 3 to 5 routers, when one router with a proper directional antenna would provide better coverage for 1/10 the cost. Or they want you to buy range extenders. These devices receive the Wi-Fi signal and rebroadcast it, theoretically extending coverage to dead zones. In practice, range extenders cut your available bandwidth in half because they must receive and transmit on the same frequency simultaneously. You get coverage in more rooms, but each room gets slower speeds. Again, this solves a problem that should not exist if the router had an adequate antenna to begin with. The global Wi-Fi equipment market generates $78 billion annually, projected to reach $143 billion by 2030. Companies like Netgear, Linksys, TP-Link, Asus, and Google depend on one business model: selling you underpowered devices and then selling you additional devices to compensate for the inadequate performance of the original device. You buy the router, then you buy range extenders, then you upgrade to a mesh system, then you replace the whole system when the next Wi-Fi standard launches. 3 to 5 purchases over 5 years. That is not a product line. That is a subscription disguised as hardware. Compare that to a $5 Yagi antenna you build once and use for a decade. The geometry does not become obsolete. Physics does not require firmware updates. A quarter wavelength at 4 gigahertz will always be 3. 125 centimeters, whether you build the antenna in 2005 or 2025. The antenna works as well on Wi-Fi 4, Wi-Fi 5, Wi-Fi 6, or Wi-Fi 7 because the frequency band remains the same. Build it once, and it keeps working forever. Here is the part that should make every homeowner genuinely angry. Modern routers deliberately prevent you from upgrading antennas. The industry transitioned from external antennas with standard RPSMA connectors to sealed cases with internal antennas you cannot access or replace. This shift was not driven by performance requirements. Internal antennas are not better than external antennas. They are worse, but they are permanently attached to the router, guaranteeing that when you want better coverage, your only option is buying a completely new device. You cannot upgrade, you cannot repair, you cannot improve, you can only replace. Some manufacturers still offer routers with external antennas, but they deliberately use proprietary connectors or non-standard mounting systems that make aftermarket antennas difficult to attach. Others ship routers with removable antennas but void the warranty if you replace them with third-party options. The message is clear. The antenna is not your component to modify or improve, even though it is in your home and you paid for it. It is a controlled interface point where the manufacturer can force dependence on their upgrade cycle. In 6 states, internet service providers include contractual language prohibiting router modification in their terms of service. The stated reason is network management and interference prevention. The real reason is revenue protection. An internet subscriber who solves their own coverage problems with a homemade antenna does not call technical support requesting a mesh system rental that generates $12 per month in additional recurring revenue. If you have made it this far, you already know more about antenna design than 99% of people alive today. Subscribe and share this with someone who needs to remember what the wireless industry made us all forget. Everything they buried is inside the complete vault. The link is in the description. Now stay with me because the next part is the heaviest. You are about to learn exactly how to build the antenna that solves your Wi-Fi dead zones for less than $2 in materials you can buy at any hardware store. This is not theory. This is not conceptual. These are the exact dimensions and step-by-step assembly instructions that thousands of people have used to double or triple their Wi-Fi coverage. You need 4 items: 12-gauge solid copper wire. A wire coat hanger works if you straighten it, but bare copper wire from the electrical section gives better results. Cost is 79 cents for a 6-foot length. You need a tape measure or ruler marked in centimeters. You need wire cutters. And you need a soldering iron if you want to attach the antenna directly to a router with an external antenna connector. Or you can simply position the antenna near your router without physical connection and still achieve most of the benefit through inductive coupling. Here are the exact dimensions for a 3-element Yagi optimized for 4 gigahertz Wi-Fi. Calculate the wavelength. Speed of light is 300,000 meters per second. Frequency is 2,400,000 hertz. Divide 300,000 by 2,400,000 and you get 0. 125 meters or 12. 5 centimeters or 125 millimeters. This is your full wavelength. Quarter wavelength is 31. 25 millimeters. Half wavelength is 62. 5 millimeters. The reflector element measures 65 millimeters, which is 5% longer than half wavelength. Cut one straight piece of copper wire, exactly 65 millimeters long. This sits at the rear of the antenna. The driven element measures 62, 5 millimeters, exactly half wavelength. Cut one straight piece of copper wire, exactly 62, 5 millimeters long. This is the element you feed with the signal. The director element measures 59 millimeters, 5% shorter than half wavelength. Cut one straight piece of copper wire, exactly 59 millimeters long. This sits at the front of the antenna. Now you need a boom to hold these elements in alignment. Use a wooden dowel, a plastic ruler, or even a cardboard tube. The boom material does not matter as long as it is non-conductive. Mark 3 positions on the boom. The reflector mounts at the 0 position. The driven element mounts 30 millimeters forward of the reflector, which is approximately 0, 24 wavelengths. The director mounts 30 millimeters forward of the driven element. Attach each element perpendicular to the boom. You can drill holes and thread the wire through, use tape, use hot glue, or use zip ties. The attachment method does not matter as long as the elements remain parallel to each other and perpendicular to the boom axis. The critical factors are element length and spacing, not how they are physically mounted. If your router has a removable external antenna with an RP-SMA connector, you can solder a short wire from the connector center pin to the center of the driven element. This creates a direct feed. If your router has internal antennas or non-removable external antennas, simply position your Yagi antenna within 1 foot of the router, pointing toward the area where you need coverage. The antenna will couple inductively to the router's electromagnetic field and focus it directionally, even without a physical connection. Position the antenna so the boom points toward the dead zone you want to cover. The elements should be horizontal if you want horizontal polarization, or vertical if you want vertical polarization. Most Wi-Fi routers use vertical polarization, so mount your elements vertically for best performance. The antenna creates a radiation pattern like a flashlight beam, concentrating signal in the direction the antenna points, while rejecting signals from the sides and rear. A homeowner in Colorado built this exact antenna from a wire coat hanger and a wooden ruler. He positioned it next to his router, pointing toward a detached garage 75 feet away where his Wi-Fi signal previously did not reach. After adding the antenna, his laptop in the garage showed signal strength increase from unusable to 4 bars, allowing reliable streaming video. His total material cost was 0 because he used items already in his garage. Construction time was 20 minutes. Compare that to a mesh network system that would have cost him $350 and required running power to an outdoor access point. Or compare it to a commercial directional antenna that would have cost $180 plus shipping. The homemade Yagi provided equivalent performance for $0 in 20 minutes. For larger spaces or outdoor applications, you can build a 5-element or 7-element Yagi for even more gain. Add director elements spaced 30 millimeters apart, each one 59 millimeters long. Every additional director adds approximately 2 decibels of gain. A 7-element Yagi with 1 reflector, 1 driven element, and 5 directors produces 15 decibels of gain and can extend Wi-Fi coverage several hundred feet outdoors with clear line of sight. If you want even simpler construction, build a cantenna. Find a metal can 90 to 100 millimeters in diameter. Coffee cans work well. Remove both ends so you have a metal tube. The length should be approximately 100 millimeters. Measure 31, 25 millimeters from the closed end and drill a small hole just large enough for your wire to pass through. Insert a wire element exactly 30 millimeters long, perpendicular to the can wall, so it extends into the interior of the can. This wire is your driven element. If you can solder a connector to it, connect it to your router's antenna port. If not, position the open end of the can near your router. The can acts as a waveguide, focusing electromagnetic energy in the direction it points. This design provides 10 to 12 decibels of gain with only 1 element and no critical spacing requirements. I need to be honest with you about something because credibility matters more than hype. These homemade antennas are not perfect. They lack weatherproofing unless you take additional steps to protect them from moisture. The wire can corrode over time if exposed to outdoor elements. The mechanical strength is lower than commercial antennas with engineered brackets and mounting hardware. If you need a permanent outdoor installation rated for hurricane force winds, you might choose a commercial antenna for its mechanical ruggedness, even though the electromagnetic performance is the same. But for indoor use or protected outdoor installations, these antennas work identically to commercial products. This is practical engineering, not commercial marketing. The physics does not care whether the copper came from a factory or a coat hanger. The signal does not care whether the boom is carbon fiber or cardboard. Electromagnetic waves respond to geometry and dimension, not to brand names or price tags. Military radio operators did not optimize for aesthetics. They optimized for what works. And what works is precise dimensions following quarter wavelength and half wavelength ratios. In 2000 BC, Egyptian metallurgists observed that shape affected energy transmission. In 300 BC, Greek mathematicians calculated the golden ratio that governs resonant structures. In 1865, James Clerk Maxwell proved the laws governing electromagnetic propagation. In 1926, Shintaro Uda invented the Yagi antenna that focused radio waves directionally. In 1997, Berkeley researchers confirmed that homemade antennas perform identically to commercial products. In 2008, router manufacturers began sealing cases to prevent user modifications. And yet a $78 billion industry would rather sell you a $300 mesh system every 3 years than teach you to bend wire following published geometry. This knowledge did not die. It was waiting in ham radio handbooks, in military field manuals, in IEEE technical journals, in the memory of people who built their own antennas before the industry convinced everyone that simple physics required proprietary technology. And now, sitting right here watching this video, you just reclaimed it. You now understand that antenna gain comes from geometry, not from manufacturing secrets. You now know that a $5 Yagi performs identically to a $200 commercial antenna. You now possess the exact dimensions and assembly instructions to build your own directional antenna that doubles or triples your Wi-Fi coverage. If this vault opened something for you, subscribe and share it. Every share preserves what the industry spent decades trying to erase. Every person who learns this is one less customer locked into their upgrade cycle. Every homemade antenna is a reminder that physics cannot be copyrighted and geometry cannot be patented. The next vault opens soon. What is inside is even heavier than what we uncovered today.